Hello everyone, I am Sayan Mukherjee from the University of Tokyo, and today I would like to talk about our work on local differential privacy preserving spectral clustering for general graphs. This is joint work with Vorapong Suppakitpaisarn, also from the University of Tokyo. So before we start, let me talk about some introduction on differentially private graph clustering. Let's say I have a social network G, then we say that a randomized mechanism Y is differentially private with privacy budget of epsilon if for any Y in the image of this Y uh, and two graphs G1 and G2 that are different by one edge, the ratio of that the output of Y on G1 equals Y, and the probability that the output of Y on G2 is what is bounded by e to the minus epsilon and e to the epsilon. And in this work, we focus on the randomized response mechanism, which, given a probability P, basically flips each edge and non-edge of the input graph G with probability P, and then it applies the clustering algorithm A, which we call A, on top of the flipped graph. So notation-wise, we can think of YP of an input graph G to be simply the algorithm A applied on the perturbed graph, G symmetric difference with F, where F is the Erdős-Renai random graph with probability P on n nodes. It is known that YP gives local differential privacy because the perturbation can happen locally at each node. So each node can flip its adjacency list before sending it to the server. So the perturbation does not need to happen centrally. There is a very famous theorem of Wang et al., which is that if this property holds between P and epsilon, then the mechanism YP is epsilon edge differential private. So what this means is that YP has a privacy budget of epsilon at least log of 1 over P. And now we bring ourselves to the motivation of why we want to consider locally differentially private clustering on general graphs. So previous works on graph clustering plus differential privacy mainly focus on the stochastic block model. And there is work on general well-clustered graphs, says Hay et al., but that works on a non-local procedure such as the SDP algorithm. On the other hand, we know that spectral clustering is robust against edge removal by the work on average sensitivity by Peng and Yoshida from 2020. And so we can ask the question, well, what about spectral clustering and randomized response? The difficulty in considering randomized response is that instead of just having edge removals, we have edge removals and additions with probability of P. And so the analysis is quite different from that of Peng et al., Peng and Yoshida from 2020. So here's our question that we aim to answer in this work, is that previous work on spectral clustering with randomized response, such as Saif et al. 2022, Heher et al. 2024, focus mainly on stochastic block models. Can we say something about well-clustered graphs? Can we loosen the requirement of stochastic block models to more general graphs? The motivation behind asking this question is that usually social networks do not follow stochastic block model. So before we move on to the main statement, let me give some background on spectral clustering and spectral graph theory. So given a graph G, we define the Laplacian matrix to be the degree matrix minus the adjacency matrix, and it is known to be positive semi-definite. And so it has non-negative eigenvalues, and its first eigenvalue is 0. Second eigenvalue is called the algebraic connectivity, and the largest eigenvalue is known to be bounded above by twice the maximum degree. Here delta z denotes the maximum degree of the graph. In our work, we define this special quantity called spectral robustness, which will be essential in stating our theorem, which is defined as some kind of gap between lambda 2 and lambda 3. So it's defined to be lambda 2 times delta over lambda 3 square. Here this delta appears because we're using the combinatorial Laplacian, and it appears as a scaling factor. So in general, the quality of cuts is quantified by this quantity called cut ratio, which is you take the cut size, but you normalize it with the product of size of S and size of its complement. And one of the main NP-hard problems in this area is to find the best alpha cut. So find the smallest alpha cut. Find the set corresponding to the smallest alpha z of the cut. Although it's known to be NP-hard to find this S star, which we denote as the optimum alpha cut, there is a polynomial time approximation algorithm which is called the spectral clustering. Here we denote this algorithm by spectral clustering 2 because we only focus on clustering into 2 clusters. How does the spectral clustering algorithm work? It first takes the eigenvector of the algebraic connectivity lambda 2, and it reorders the vertices of G in such a way that the second eigenvector components are in increasing or decreasing order. This is known as the spectral ordering of Z. And then it returns a cut, a contiguous cut, S comma S bar, where S is some I0 that you cut linearly in the middle of this spectral ordering. And the main kind of good thing about spectral clustering is that instead of searching over all of the possible cuts, you only have to check which is the smallest cut among a linear number of possibilities. Okay, now we can move on to describe our main results. First, we define what we mean by a well-clustered graph. In our case, the input graphs we assume all have high maximum degree, which is in particular the maximum degree is at least 10 log n times lambda 3. Usually this is a very loose requirement because delta is at least lambda n over 2, and also usually social networks have nodes which have very high degree, which are also called supernodes. The next assumption we make is that there is a gap between lambda 2 and lambda 3. And that assumption is quantified by this eta z being small. Moreover, we assume that there is that lambda 2 is at least some constant. We note that this 1 over 10 here is quite arbitrary and it can be replaced with any constant. and we will just have new constants in the rest of our arguments. Same with this 10 log n. The third answer, the third assumption we make is that the graph has big clusters. So what this means is that the minimum alpha cut, the minimum balance cut of G and G delta F both have at least n over 10 vertices. Again, this 1 over 10 is quite arbitrary, and we can replace it with any constant we want. Now we go on to state our main theorem, which is the robustness. So here, let's say our input graph is well clustered, and we flip the edges and non-edges with probability log n over 10n. Then with very high probability, the spectral clustering output on G delta F remains close to the spectral clustering output of G. How close? The number of misclassified nodes, which we denote as d size, is going to be at most order of eta z times n. And because eta z is typically very small, so our result implies that publication of spectral clustering on G delta F still retains utility. On the other hand, we show a tightness result, which is that there exists a family of well-clustered graphs such that if you flip with probability much larger than log n over n, asymptotically larger than log n over n, then the spectral clustering on G delta F doesn't give anything useful and is very inaccurate. Although because G was well clustered, so SC2 of G was pretty good. Okay, so now let me show some sketch of our proof of robustness. First, we introduce some notation, which is that spectral clustering of on the graph G, let's denote the output of spectral clustering on G as the cut S comma S bar. And on G delta F, let's say the clustering algorithm outputs SF and SF complement. And let's denote by S star and SF star the optimum alpha cuts of G and G delta F. And the number of misclassified nodes between S and any other set F prime is defined as d size. This is twice the minimum of the symmetric difference between S delta S prime and S delta S prime complement. So however many nodes are misclassified. And so because this defines a metric, we can use the triangle inequality. So the difference between S and SF is at most the difference between S and S star plus S star and SF star plus SF star and SF. So by triangle inequality, we can break the upper bounding on each of on this entire quantity into 3 steps, which are 3 upper bounds on each of these quantities. And we do that separately for each of these terms. Our first term is basically a statement about accuracy of spectral clustering. Although it's not related to privacy, we show a sketch of how to bound the discrepancy of spectral clustering. First, we recall that Ziegler inequality shows that lambda 2g over n is at most alpha g of the optimum cut. And we note that there is an improved Ziegler inequality of Kwok et al. From 2013, which shows that alpha z of the spectral clustering is bounded above by this thing, lambda 2 times square root delta over n times square root lambda 3. And together with the lower bound of the Ziegler, if we replace lambda 2 over n here, we get alpha g of the spectral clustering output is at most this factor, square root delta over lambda 3, times the optimum alpha value. Now we employ a stability result of Peng et al. 2015 that says that if alpha g of s is at most some factor times alpha g of s star, then the discrepancy, the difference between the two cuts, is bounded above by uh, this term times the factor times n. If we simplify this a little bit, we obtain that the size of S and S star is bounded above by eta z times n. And so that finishes the first term. Now let's think about the second term, which is SF and SF star. So by the previous slide, we know that this discrepancy is bounded above by eta of z delta f times n. So it suffices to show that eta of z delta f is bounded above by some constant times eta z. So we'll show this in three parts. First, we will bound the lambda 2. So note that lambda 2 of the symmetric difference is less than or equal to lambda 2 of G union F. And by the fact that lambda 2 can be broken over two subgraphs that are disjoint, we know that this is at most lambda 2g plus lambda 2f minus g. Now what is f minus g? F is an Erdős-Renai random graph of probability p, which is p less than log n over 10n. Because this is less than the connectivity threshold for Erdős-Renai graphs, we know that lambda 2 of f is 0 with high probability. And so that implies that lambda 2 of g delta f is at most lambda 2 of g with high probability. On the other hand, when we compare lambda 3, we can show that lambda 3 of g delta f is at least lambda 3 of g over 10 with high probability. And the way we show this is by first showing that the Laplacians of g delta f and g are pretty close, bounded by twice delta f. Then we bound the maximum degree of this Erdős-Renai graph with 9 log n with high probability using Chernoff bounds. And what this implies is that the true norm of the difference between Laplacians of g delta f and g is bounded above by 9 log n. And 9 log n is at most 9 over 10 lambda 3 of g by our well-clustered assumption with high probability. And by the Weyl inequality, what this implies is that the eigenvalues also differ by at most 9 over 10 lambda 3 of g. And that implies this bound on this relation between lambda 3's of the perturbed graph and the original graph. Next, we also have to show a perturbation result for the maximum degree. And this follows from Chernoff inequality and the union bound that the degree of any vertex in the perturbed graph is at most the degree of the vertex in the original graph plus the maximum degree of G with high probability. And that finishes the bound on the second term. Now for the third term, it is the most technical part of our proof. We use Hefting's inequality and some conditional probability arguments to show a technical lemma, which basically says that if we have a constant such that alpha g of SF star is at least the constant times alpha g of S star, then the probability that the same direction holds for alpha z delta f is very small. So what I mean by this is that for this particular choice of gamma 0, if alpha g of SF star is less than the constant times gamma 0 of S star, then we can use the stability of the cut, the optimum cut in G, to upper bound the t size of SF star and S star. On the other hand, if the other direction holds, which is the one of the hypotheses in our technical lemma, then what happens is that in G delta F now, in the perturbed graph, S star satisfies the stability requirement for SF star, which is the best min cut in the perturbed graph. And then using stability in Z delta F, we can then show that the size of S star and S star F is at most bounded by at most constant times a tau Z delta F times N. And by the previous slide, we know that the robustness of Z delta F is at most some constant times robustness of G. And that finishes the proof of our main theorem. Now we show a proof of the tightness of our main theorem, which is we construct a family of random graphs with three parts, A, B, and C, such that G satisfies the conditions of well clustering. So here what we do is we take n vertices and we divide them into parts of size beta n, 1 minus beta n over 2 and 1 minus beta n over 2, and we select beta to be at least 1 over 10 so that we satisfy our smallest min-cut condition. Next, we add edges between every pair of vertices in A and B with probability 1 over 10n, A and C with probability 1 over 10n, and B and C with probability log n over n. And we add edges inside A and C with some constant times log square n over n to make it denser than log n over n. And we add edges in the interior of B with some probability log n over n. So the minimum cut in this graph is known to be, it can be seen that the minimum cut is A and B union C. And what else can we see from this graph? We can see that lambda 2 of the expected value of the Laplacian is going to be 4 over 10. For specific details of these calculations, please refer to the main paper. And we can show that lambda 3 is of the order of constant times log n. And this implies that this family of graph satisfies assumption on well clustering assumption with very high probability or in expectation. And because the expected Laplacian and the Laplacian of a graph are close enough in spectrum by the work of Chung and Radcliffe, for example, we can say that the graphs from this family satisfy the well clustering assumption with high probability. But what happens when we flip edges and non-edges with probability p is that the 1 over 10n becomes p. Uh, all of these 4 over these log square n over n become the whatever is the maximum of p and log square n over n, and all of these log n over n's become p, basically p minus little of p. In this new graph we can show that the lambda 2 of the new graph is basically Pn plus some 1 minus 2p times lambda 2 of the original Laplacian expectation. And lambda 3 also scales similarly. And because this transformation happens, the point is that as Pn is greater than log n, so this is the dominant term in both the numerator and the denominator, and so this limit is 1. So in G delta f, the Laplacian gap basically vanishes, and therefore spectral clustering will not give any good results on the clustering output. Now we test our algorithm on the different graphs, real networks obtained from the SNAP database by Leskovec and Macaulay. Here we show a Facebook graph which is 0.edges in their files, which has where we prune degrees of nodes of degree less than 10. After pruning, we're remaining with around 120 edges, vertices, and we can see that there is a very clear two clustering of the graph. And we show on the left the graph and on the right the graph after flipping. We can see that cluster structure is somewhat preserved, even though the neighbors of this node 86 are placed in some different clusters between on the left and on the right. Note that when n is 120, the log n over 10n in our theoretical bounds is around 0.0039. But when we look at the worst d size of S and SF, so worst discrepancy between spectral clustering on G and spectral clustering on G delta F, we see that the clustering results are actually very stable until 0.005. And even for higher flipping probabilities, the clustering result still remains quite stable. Note that these values are the raw discrepancy values and not normalized by the number of nodes. Next, we also considered the Facebook 1684 graph, which after pruning has 574 nodes. It has 3 clusters. The nodes 0 to 15 are a small cluster, and then 17 to 200 is another cluster, and then the remaining graphs are the third cluster. And spectral clustering initially gives this as the clustering output. For this graph also, when we look at the worst discrepancy, we get very stable results. And when we look at average discrepancies, we also get very stable results. Note that log n over 10n, even though it's around 0.0011, we can go up to even 0.1, maybe 0.04 for very good clustering stability of spectral clustering. So let me conclude this with some final remarks. First, we show that spectral clustering and randomized response achieves a privacy budget of log n. And we construct a family of graphs that requires the privacy budget of log n to show that our theorem is tight. And we observe that for real networks in practice, the flipping probability can go actually quite higher than log n over 10n and still preserve the clustering results. And generalizing to our work to more than 2 clusters is quite challenging because of the technical lemma that we use to bound the third term. But if that kind of bound can be obtained, then our work can be extended to more than 2 clusters. And that's it. Thank you for your attention.